So now in this example, let's look at in real world example why this normalization and standardization is very important. So look at this table here. We have two features. One is age, another one is salary, right? Age ranges from 25 to 50, and salary is from 40,000 to 120,000. So as individuals, like a human beings, if we see, that's fine. We understand this. These two are just two different units. Like one is years, another one is like a dollars. But to a machine learning model, everything is just numbers. They just look at this as a numbers, nothing that much. The model doesn't know that 120,000 is a salary and like a 50 is an age. It only sees the magnitude of these numbers, which is the highest number, something like that. So if you feed this raw numbers directly, the model might think that salary is much more important simply because the values are very larger. It gives higher weight to features with the bigger ranges, and that becomes a numerical bias. So, as I previously mentioned, if we train a model to predict the job performance, it might assume that salary with 10x more influences than age. Just because 120,000 is like very high salary, it will give that as the high performance. So that's why we standardize and we actually normalize. So what normalization, as we previously saw, this is a normalization for the age. Here we did the same thing, x minus x min by x max minus x minimum, we get 0.11. And if we do the same formula, we get 0.29, 0.641, and all the things. And same, the normalization is for this one, 40,000 minus x minimum is 40,000, which is 0, and you get this one. Now if you see the standardization here, on the other hand, it sends the data from 0 and expresses values in terms of how far they are from the mean. So this way, every feature has a mean of 0 and a standard deviation of 1. So we can say, for example, a person A's salary is 1.4, right? We can say as 1.4, the standard deviation below average, while person D's salary is 1.5, something like that. This makes comparison more intuitive and fair regardless of the original range. So the misinterpretation is that without scaling, right, the model would think that features with bigger numbers, right, 120,000 or something like that. By applying normalization and standardization, always columns by column, to ensure every feature contributes equally. The model now focuses on relationships, not raw magnitudes. So that's what's happening here. And I can also talk about other examples in like the standard and the one thing is that the issue which we actually face in here is, uh, let's see, age is 36.75, standard deviation is 10.8, and mean salary is 80,000 and standard deviation is 28,000. So for normalization, we can use like neural nets, bounded inputs, and for standard linear, logistic regression and stuff. So one of the key differences between normalization and standardization is that uh, the output range usually for normalization is 0 to 1. There's no fixed range for standardization. It may be 0 or 1. And normalization is very sensitive to outliers. As I said, if you increase the value, it could go out of this 0 to 1 range. And this is less comparatively. It's also sensitive, but it's comparatively less. Use case neural nets, bounded input and regressions, algorithms, things like that. And I just want to give like one more example for the standardization and the normalization, like how the misinterpretation of the numbers could happen. So let's say we are building a machine. Uh, let's see, to predict the by age of numbers and salary that he's going to buy a car, right? So to see, if we see that 25 to 50 is a small range, and this 40,000 to 120,000 is a huge range over here. To us, it's obvious that someone's age and income both matter in buying decisions. Maybe like, younger people prefer sporty models and higher income buyer prefer luxury models. But the model salary has a much bigger numbers, like tens of thousands. So what happens? So this model, what it thinks that the salary is far more important simply because it's a big number. It thinks that someone earning 120,000 will definitely buy a car, and you could target the wrong customers. Meanwhile, it might ignore the subtle patterns like the age and the other ones. So this model confuses the scale of the number with the importance. It's not making a smart decision. So by normalizing what we do over here, if you normalize these values, it is between the range of 0 to 1. You see, normalized values are always between 0 to 1. Okay. Now, age and salary are both just a small numbers. It is between this 0 to 1, representing their relative positions. The model here, it no longer gets distracted by big salary issues or big age groups or anything. For example, maybe people aged between 30 and 35 with moderate income, right? They are the one who are most likely to buy. And same thing if we see with standardization, we measure how far each person's value is from the average. So if the mean salary is $75,000, right, like, or mean salary is $80,000, a person earning $120,000 is plus 1.5 standard deviations. His deviation is this one. That tells that model that the person earns more than most people, not the number. 120,000 itself is the most important. So yes, what I mean to say is, if you don't scale your data, your model might incorrectly assume that a person with 120,000, the guy with 120,000 will buy a car simply because the number is big. So normalization, standardization prevents that actually by bringing all features to a fair comparable model within the 0 to 1 range, letting the model focus on real relationships, not its magnitude. So that's it. And thank you. We'll see in our next videos.